Hello, everyone. This is Professor Wei. Let's continue our discussion on discount cash flow framework. So in this video, I will walk you through a few examples in the Excel environment. After this tutorial, I believe you will have a better idea on how to use Excel to solve for discount cash flow type of problems. Also, you will gain a big picture on how to move money through time practically, because we all know that a dollar today is not equal to a dollar tomorrow. Okay. Also, I believe you will get a better idea of cash flow patterns and the DCF framework in general. It's very important and it's indispensable for our subsequent analysis. Moreover, I think at the end of a tutorial, you will have a feeling that there's sort of a limitation on the Excel. That's why after this week's lecture, we are going to move on to the Python platform because the Excel is quite limited in terms of solving for advanced or more complex computing problems. So after this video, after this lecture, I highly encourage you to revisit all the examples I showed you without looking at the answers I posted, okay? It's gonna be very healthy for you to digest all the problems I go over, okay? So once you are comfortable with all of these type of basic problems, you will be able to move on smoothly. Okay, so let's delve into the very first example problems. Okay, so well, we all know this is a very standard present future value identity. Future value is equivalent to the product of present value and the future value factor, which is 1 plus the interest rate to the power of time frame. Okay, it's kind of straightforward. So suppose you have the initial investment of 6,000 and the investment period is 5 years and the rate and on the annual basis of, is 7%. Now you're going to calculate at the end of the investment horizon, what's going to be the future value. Okay, so it's kind of easy. You can use your financial calculator or Excel to solve this type of a problem using the function embedded in the Excel environment, or you can just use this Finance 101 formula here on my slide. So if you want to use the Excel formula here, you have the FV functions. FV function, basically, there are four components over here. First one is the rate. In this case, it's the annual rate of 7%, and you have the number of compounding period, which is 5, and you have the payment, in this case, is 0. And here we have the PV. Notice that we have, well, I input a negative sign over here. This is because it's sort of a, initial investment, which is an outflow in this cash flow diagram. Okay, so, well, if you drop this negative sign, you will find out the sign on the future value is switched. Nothing wrong over here. It just depends upon how you think, inflow or versus outflow. Okay, that's kind of intuitive. Nothing wrong on the sign. So let's move on to the second example. So suppose you have the future value of $2,000 and number of investment period is going to be 9 and interest rate 11%. What's going to be your present value? Well, of course, you can use the formula over, the formula on my slide. So basically, you discount back all your, the single cash flow 9 years from now to the present. So that gives you your present value. Alternatively, you can use the Excel function. So essentially, you discount back your future value, your future cash flow to the present by using this function along with these 4 inputs. The first one is the rate, same as the previous example. The number of period in this case is 9%. Payment, again, it's 0. We don't have the annuity component over here. Now we have the future value. Again, notice the sign, I put a negative sign over here just to ensure the readability of the result. If you drop the negative sign, it's going to be negative. Well, it just depends upon how you think about it. Well, to disentangle the cash flow, well, in this case, I just do it a little bit in a overly engineered manner. So basically, I draw a timeline over here. Okay, so I intentionally leave all the intermediary cash flow to be 0. And I do it period by period. So it's kind of a replication process. Oops. So basically, I discount back all the I sum up all the discounted value each period. Now I have the total present value. But in this case, all the intermediary cash flows are 0. So that doesn't change the dynamic. But after, later on, you will see a few other examples which are more complex, which require your intermediary inputs to provide better visualization of cash flows each period. So, but anyhow, this is just a sort of a visualization process. Okay, so the idea is to present you the timeline of this whole process. You only have one single cash flow in this universe. Okay, quite straightforward. Now the third one is also pretty easy. So basically, I want to illustrate the idea of the perpetuity. So basically, you have the investment opportunity like this. So every single period, you will receive $800 from whatever instruments like preferred stock or fixed income security. Every single year, cash flow level 800, the required rate of return is 9%. Now, how do you evaluate this asset? Well, essentially, you just need to use the perpetuity formula. Just take the ratio of the cash flow level and the discount rate. That will give you the present value or discounted value of all the future cash flows, which is at this level. Now, the main point I want to show you is that for any type of perpetuity, essentially the first 100 terms, the first 100 individual terms, their present value actually takes up more than 95%. Okay, so if you look at this cash flow diagram, I input all the intermediary cash flows here, okay, under the B column. So I discounted back every single cash flow, every single period, okay? So each period I discounted back to the present. So you can see the subscript, oops, you can see the number of period is basically changing over time. It's gonna be the where is it? A13. Yeah, there we go. So I basically create this dynamic. Okay, so the number of period is changing. So the idea is I bring back all these intermediary cash flows to the present. Now, if you look at the first 100 terms of the present value, let me do a quick summation for you. Give me a second. If you look at the first 100 terms, actually the present value is pretty close to the real present value of this perpetuity. Okay, because you can see after after the first 100 terms, the discounted value is actually very little. Why is that? Well, that's because this time component serves serve as the exponential. So a change a little bit over here can disturb the result quite a lot. So that's why the subsequent components of your future cash flows is kind of trivial in terms of the impact on your total value of the discounted cash flows. Okay, so that's just one thing I want you to visualize. Now, let's move on to the annuity example. So suppose you have an annuity that pays you $400 every single year for the next 15 years with an annual rate of 7%. Okay. Now, how to establish the value of this annuity? Well, you can obviously you can use the Excel embedded function, which is the present value function, same with the previous two examples. So the idea is basically you input the rate, number of period as given, and the payment over here, and drop the future value component. In this case, we don't have any future value in this context. Right? So it's pretty simple as it shows. Alternatively, you can disentangle the cash flows by drawing diagrams like this. So basically you input all the intermediary cash flows, basically is the $400 listed over here, and discount back each individual cash flows, okay? Every single period you do that, discount back every single cash flows to the present and sum them up. You can have the present value of this annuity asset. Okay, very straightforward. So let's change the dynamic a little bit. What if I change this question to be an annuity due type of a problem? Okay, so essentially we move the cash flow one period backward. Okay, so notice that on this timeline, in the previous example, I intentionally leave the first, or actually the 0 period blank, because every single cash flow occur at the end of each period, which is the definition of the annuity due type of problems. Okay, sorry, ordinary annuity problem. So for ordinary annuity, each cash flow occurs at the end of each period. Okay, for annuity due, well, it's basically the type of this type in this type annuity due, basically cash flow occurs at the beginning of each period. Okay, so there is one period lead-lag relationship. If you use the Excel function, notice that here for the fifth component, which I didn't show you for the previous example, basically the value of 1 is an indicator variable that tells Excel this is an annuity due type of problem. Okay, so if you input that, that will give you the value of this annuity due, which is 38.98. You can see it's actually greater than the ordinary annuity, simply because of the monetary value attached to time. You have one period of you have one period backward. So basically you save one period of a discounting process. Okay. Also, you can use Excel to solve for the future value type of problem. It's kind of similar. I don't have much comment on that. I will save this example on page 32 of my slide for you. You can try to play with the Excel to see if you can get the number. Okay, it's kind of similar. Now, let's take a look of another annuity payment problem. So basically, let's assume you retire in 35 years and you want to have $2 million saved up at the end of the horizon. Okay, so with the same 8% of interest rate as before, how much you will need to deposit each year to reach your goal. Okay, so there are two alternative ways to solve for this problem. Well, first one is to use the Excel payment function. Okay, so basically you can input the rate, number of period, present value, future value. Then you back out the payment component. Okay, so I don't think it's very hard to implement, but I do want to show you actually Excel solver can address this problem as well. You may think why I want to overcomplicate this process. In fact, it's not an overcomplication because in the real world, this type of problem can be a little bit complex. Sometimes the Excel or your financial calculator cannot take care of this type of problem accurately. You have to customize or tailor this sort of analysis in terms of the intermediary inputs, the intermediary cash flows. Okay, in this case, I still assume there are not much variation over here. Just want to visualize the implementation. But later on, you will see the example is getting more and more complex, which simple Excel function cannot take care of this type of problem easily. Okay, anyhow, if you want to use solver, what you need to do is to set up this timeline and set up the intermediary cash flow, okay, and build up the future value component using the the 101 formula. So your present value, which is the intermediary cash flow in this case, in this period, times 1 plus the interest rate. Notice I use the dollar sign as the absolute referencing over the power of the time frame for that particular period, which is the difference between the 35 and the one which is 34 years. Okay, so by doing so, I create the dynamic for each period. Okay, after you build up the formula for each period, okay, you can use the solver to address the problem, to solve for the objective cell, which is the saving amount. Okay. Oops. Let me close it. So try to play with that after you watch this video. Okay. So the point is, the key part is to input the formula. After you input the formula, all the all the cells will still be blank because this is the because the objective cell is still empty. Oops. Okay, so basically you want to solve for it. Let me repeat the process. Oops, why is so slow? Oh, okay, there we go. Okay, so you can see the numbers are identical. Okay. All right, so let's take a look of another a more complex example. Okay, so suppose there is a deferred time frame. Okay, so basically, if you do not save anything for the first 14 years, how can you evaluate the level of your saving amount? So it's sort of a deferred annuity. Okay, so if you draw a timeline, nothing happened for the first 15 years. The first cash flow occurs at the end of the 16 years. Okay, so well, actually, it's still the same process. You just need to set up the intermediary cash flow and discount back each component and use the solver to back out the number. Okay, get some practice in that regard. The other two things I want to highlight is you can also use the Excel number of a period function to determine the number of period, which is NPER. So you can see you have the rate, payment, present value, future value. Again, you need to make sure the sign to be consistent. Otherwise, there will potentially be some sort of an error. Let me see. Also, I think I have a rate problem. So basically, given the future value payment and the number of period, you can determine the required rate of return or the interest rate for the problem using the RATE, which is the rate function in Excel. Very simple. I'll leave that for you. Okay. Now, let's take a look at a few more complex examples. Okay. Let me open it up for you. So this is a typical deferred annuity problem. Typically, it's it sort of fits into the context of a retirement plan. Okay, so suppose you want to retire in 35 years. Okay, after the retirement, you want to have this amount of money per year for 25 years. Essentially, you want to get a cash flow at this level. Okay. Well, you expect to earn 4.5% on the annual basis during the retirement stage. Now the question is asking you how much you need to deposit each year for the next 35 years, assuming you earn 7% on your savings. Okay, save this for a moment and think about how to solve for this problem. Okay, please pause the video for a second and think actively how you address this problem. Okay, now, so essentially, this question is asking you the level of the cash flow you need to deposit at each year on your retirement stage. Okay, so basically you need to set up a cash flow diagram like this with 4 columns. So first you want to visualize the cash flow pattern in the first place. Okay, so the total investment horizon is going to be 60 years under this context, right? 35 plus 25 is going to be 60. So at year 1, the beginning balance is going to be 0. Okay, so the intermediary cash flow is going to be the number you are going to solve for, right? So the ending balance is the level you deposit times 1 plus the interest, so 1 plus the required rate of return during the working years plus the beginning balance, which is 0 in this case, right? Likewise, you can replicate this process for the entire working years. Okay, so for the entire time frame from T0 to T35, basically you employ the exact same formula. Okay, so basic present future value relationship for the D column from D14 to D49. You are basically using the same formula. So bring the money from the present to the future. You calculate the ending balance each period. Okay, you do that intentionally. Now, the tricky part is over here. So starting from your retirement stage, basically you have to withdraw or spend 130,000 every single year because you're retired, right? You probably need to spend more. So basically, this is a pre-specified input. You have to replicate the previous process over and over again to the end of the investment horizon. The most important thing is to use the solver to solve for this objective cell. Okay, so now I want to show you one thing, which is the objective in this case is D74, the ending balance. Okay, so think about this. For the entire retirement plan problem like this, basically the ending balance is 0, right? So that's the objective of our analysis, right? So basically, at the end of the horizon, you spend up all the money you deposit during your working years. Okay, so on the second stage, basically, there are only cash outflows. During the initial stage, there are only cash inflows, right? So essentially, this solver thing can help you to even out this present future value relationship on the inflow and outflow context. Okay, so basically you set the objective of ending balance to be 0, then back out the objective cell, which is the saving amount per year on the initial stage. Okay, actually, this is similar with the Excel circularity feature. Basically, you replicate the process each period and back out the number you want to solve for. Okay, now there is one more problem that can be a little bit more complex, which is the sort of a deferred growing annuity. So it's the intersection between the growing annuity and the deferred annuity. Okay, so let's take a look at the details. So you want to retire in 35 years. After retirement, you want to spend same 130,000 per year for 25 years, and you expect the cash flow growing. You expect to earn 4.5% during your working years. So the question essentially asking you how much you need to save each year for the next 35 years, assuming you earn 7% on your saving account. Okay, and suppose you increase your saving amount 4% each year. That's the difference between this example and the previous example. Okay. Now assume your 130,000 needs to grow by 3% a year to offset inflation. How much is your initial saving amount now? Okay, pause the video for a second and think about the context of this problem and try to make the distinction between this example and the previous example. Okay, I'll give you a few seconds. Okay, so now with a similar setup, you need to draw a timeline or time value diagram, something like this. So basically, the beginning balance, again, it's 0 at the beginning of the timeline. The intermediary cash flow is the objective cell you are going to solve for. And the ending balance, well, same construct. That's the, the basic present future value identity. You do that for the entire working years. Now, you want to realize that the intermediary cash flows is changing over time because you deposit more every single period. Okay, so this is a growing annuity. Okay, so basically every single year you can see the level of the cash flows changing over time. Okay, for the first 35 years. Now, for the retirement stage, so after the first 35 years, starting from T36, you will see the spending amount is also growing over time. Okay, that's a major distinction. So essentially, in this problem, you actually combine two streams of cash flows, which are both growing over time. Okay, so you really want to balance out the inflow and the outflow in this context. Okay, so that's the primary difference between this example and the previous example. Again, the objective is to eliminate your ending balance, to eliminate the ending balance. And by eliminating the ending balance, I mean you want to zero out this Excel by using solver. Okay, now you can see it's not 0 over here. That's because of the rounding error. If you do that again, it will completely be eliminated. Okay, so that's the primary distinction between these two examples. Okay, so another comment I have on this example is that you can see if you want to address this problem, it's kind of hard for you to use the Excel function. Maybe you can, but that's not very helpful for you to disentangle the cash flow and to visualize the cash flow pattern. Because by creating this diagram, you actually can, look up each year's individual cash flow, which is very, reader friendly. But I do have another comment, and that is this process is kind of a labor intensive. You have to manually draw this diagram, and you have to, use your mouse or trackpad to, drag the cell, and it's not something easy to replicate, and it's not something easy to, it's not something scalable, which means that I cannot do this thing at a very large scale. For example, if I'm working for my clients, I want to, generate this process at very large scale. For example, I want to produce a report like this 10 times or 20 times. Actually, I can write a small program, do that very easily. I can automate this process by using programming to improve my working efficiency and productivity. Okay, so that's sort of a motivation for you to learn Python in our future lectures from now on. Okay, so basically, probably 2 weeks or 3 weeks from now, I will teach you how to how to write user-defined functions to capture the time value calculation. So basically, you can design your own financial calculator to to automate the process, which is very useful and very productive. So I personally am not a big fan of Excel because I just feel like it's outdated. It's sort of a labor intensive. But I have to teach you this because this exercise is are really helpful for you to visualize the cash flow patterns and get a better idea of how to, disentangle the cash flows. Okay, so that's the idea why I want to go over these fundamentals for you. Also, by working through these examples, you revisit the most important notions in the financial analysis, which is the discount cash flow framework. Okay, so there are a few other examples, but I think you should be able to solve all of them on your own because nothing hard over there. Oh, actually, there is one more example I want to talk a little bit. Uh, so let me find it. Okay, so that's the example I do want to go over real quick. So suppose you have, you have a sequence of cash flow like this. You have 5 investment periods. You can see the level of the cash flows are different. Okay, and given the interest rate, how to evaluate this asset. Okay, in Excel, you have another function called the net present value. Okay, so basically it allows you to bring back this stream of uneven cash flow to the present. So my comment on this is the net present value in the Excel environment is kind of a different from our traditional, our textbook defined NPV. Okay, so in your previous introductory level finance class, our NPV is the difference between the present value of future expected cash flows and the initial outlay. Okay, so for example, if you are working for a company which is planning to invest in a long-term asset, okay, so this long-term asset is going to generate cash flows at a level like this, and well, since you have to finance your investment, you have to incur a certain level of initial outlay, right? So to evaluate this process, you have to take the difference between the discount cash flow present value and the initial outlay. Okay, so it's a difference between two numbers. But here in this Excel environment, the NPV essentially just the summation of the discounted value of your uneven cash flows. Okay, so conceptually, it has nothing to do with the initial outlay in the Excel environment. So in the future, if you are working with other problems, this is something you want to be aware of. Okay, so if I make this example more realistic and I introduce the initial investment component. For example, I ask, let me complete a story. So suppose this investment on the long-term asset cost you an initial outlay of 55,000. Your NPV, your net present value, NPV for the outside shareholder is going to be the difference between the present value you got from your previous calculation and the initial outlay, which is negative. Okay, so you can see it's a negative number, which means that it's value reducing to the outside shareholders. And as a rational decision maker, you have to turn down this project. Okay, so the reason why I want to show you this, just want to highlight the difference between the Excel function and the financial definition of NPV. Okay. Other than that, I think you should be able to. I mean, I think you are fully you fully understand the all these examples. Okay. All right. So that's all what I have for today's lecture. Like I said, at